Hello, this lecture will cover pages 153 through 158 of my lecture notes. Please print those pages out and have them in front of you as I present this lecture on flip-flops and related devices. Part B, the gated SR latch, digital pulses and clocks. Starting on page number 153, we're going to mention as our third flip-flop the gated SR latch. We've already talked about the first flip-flop, which was the NAND latch, the second flip-flop, which is the NOR latch, and now we're going to talk about the gated SR latch. Notice that this particular flip-flop here comprised of a latch, and it has two NAND gates in the front end with an enable signal feeding both of them. This is referred to as steering circuits. We'll talk about that in a later lecture. But we have a typical NAND gate latch, which is low active. This is a low active set. When this signal goes low here, that's going to set the flip-flop. And when this goes low, it's going to clear the flip-flop or reset the flip-flop. Q bar just does the opposite of what Q does. So everything is defined by Q. Remember that. So back here, if you take a look at the truth table, in order for this flip-flop to work, enable has to be a 1. There has to be a 1 on enable, so it turns this gate on and turns this gate on, or it enables this gate and enables this gate. The 1 at that pin here and the 1 at this pin here will enable these gates. And notice it places an inversion. If this was a low active set, this will be high active set here. If this was a low active reset or clear, this will be a high active here because the NAND gate basically gives it an inversion. So looking at this very closely, the block diagram of this simply looks like a high active set and a high active reset with an enable circuit, with an enable. So basically what we'll see is this. There's our flip-flop. Here's our Q output. Here's our Q bar output. Here is our enable, high active. This right here is our set. And this down here is our reset or our clear. High active. High active. High active. That could be clear or reset. Either one doesn't make any difference. Clear or reset means the same thing. I mean, that's the block diagram for this. But the truth table explains that. And then the ambiguous or the not allowed state is when they're both ones. You can't be saying set and reset at the same time. So right now, that's not allowed. A 1-1 condition's not allowed. 0-0 is no change. A 0-1 is clearly a reset. A 1-0 is clearly a set because these are high active now because this gives us the inversion. Still low active in here because it's a latch. Still low active in here, but they make these inputs high active. If you look on pages 227 and to 229 of your textbook, you might have a different version textbook, so let me look at page 227, see what it looks like. This example right here, this is what we're looking at. Assume that Q0 initially, Q is equal to 0 initially, and determine the Q waveform for the NOR latch. Just make sure you find this in the book. And you're looking at the NOR latch on this case right here. This is your set input. This is your reset input. The NOR gate latch is high active. So whenever set goes high, the output goes high. Whenever reset goes high, the output's reset. The ambiguous state is when they're both high at the same time, and they won't be. The author's not going to try to trick you there. Then you have the next example right after that. They talk about in this book, figure 512 shows a simple circuit that can be used to detect interruption of a light beam. Just make sure you look that over. This is what the circuit looks like right here. Real easy to understand. The alarm will go off. When's the alarm going to go off? Well, as long as there's light on that photocell, as long as there's light on this photocell right here, this output's grounded. This is low. Okay? And with this switched in, they're both low. There's no change out here. This is low, inactive. Well, as soon as the light is blocked or interrupted, somebody walking through a doorway and this light hitting this photocell gets interrupted, this turns off. When this turns off, it pulls set high. When set goes high, the output Q gets set and the alarm goes off. They talk about this, the problem there in this chapter. Also, the next example, 5.5, really good circuit right here. Explain its operation. Basically, all you're going to do in this circuit is take the 1 kilohertz signal and you're going to pass it through to output A, to output X sub A, or you're going to pass it through to output X sub B. And this switch makes that choice for you. When you're in position A down here, what you're doing is you're setting Z1, pin 3, to a 1. You're setting this. Pin 2 goes to a 1. With pin 2 goes to a 1, you're enabling this upper gate. And the 1 kilohertz signal goes through pin 1 to the output. Notice that when it's in position A, you put a 1 up here, but you're putting a 0 down here. You're setting this flip-flop. Setting it here enables this, a 0 down here disables this, so this is turned off down here. This output's always going to be low. Then in position B, what you're doing is you're clearing this flip-flop. You're putting a 0 up here, which turns off this one. You're putting a 1 down here, which enables this. So the 1 kilohertz signal goes through pin 4 of Z2 and comes to the output X sub B. Just make sure you look over that circuit and you understand how it operates. Just using the latch to do that. Example 5.6, which is the next example, I think you'll find that useful as well. Make sure you look that over. Page 155, we're going to mention digital pulses and clocks real quick because we're going to start going in that direction. First of all, pulses. Pulses have a finite rise time in them. You'll see them drawn like this. That's a finite time from low to high. So we're going to make it look like this. And the pulse, if a pulse goes high for a certain period of time and goes low, or it can go low for a certain period of time and go back high, we're showing it this way. But I want you to notice that the pulse width is measured from the 50% point. It's pretty easy to get that 50% point going high and the 50% going low. That's referred to as the pulse width. The rise time of the pulse is measured from a 10% to 90%. That's the rise time, T sub R. And you'll see in the specifications T sub R for rise times. The fall times, T sub F, that should be a T sub F right there, goes from a 90% to the 10% again. That is the fall time. That's for a positive going pulse. Just some definition there. Look down here. They talk about leading edge or rising edge, trailing edge, and falling edge. Well, the leading edge is the first edge you see. And in this case, it's a rising edge. The trailing edge is the latter edge. And in this case, it's a falling edge. But the leading edge isn't always the rising edge. And the trailing edge isn't always the falling edge of a pulse. Let's look down here. For a negative going pulse, the leading edge is a falling edge here. And the trailing edge is a rising edge. So just a little terminology. In the book, you'll see something called NGT. It's a negative going transition. Okay, so it's always the falling edge. So the NGT on this positive going pulse up here is right here. I'm sorry, the negative going transition in the positive going pulse is right there. In the negative going pulse, it's the leading edge right here. And the PGT, which is the positive going transition, is the rising edge up here, and it's the trailing edge down here. So just make sure you understand what they mean by NGT and PGT. Clocks. If you take a look at page 56, there's clock A. We have clock A. Let me put it down here. There you go. I think you can see that. There's clock A. Positive going clocks. There's your positive going transitions. I labeled them with arrows. You might want to do that in our timing diagrams coming up. That's what it's going to look like. If I say label the positive going transitions, that's the way you'll do it. Down here, clock B. Clock B looks like negative going transitions. There's your negative going transitions. So we're labeling our negative going transitions. In both cases, you can see what T is here. Let's put a T in there. The period. There's the period for the positive going clock. This one starts repeating itself from here to here. Here's the period for the negative going transition, so negative going clock, clock B. The period is in seconds, and you know frequency is equal to 1 over T. So if you know what the T is, right here you invert it, you can get the frequency in hertz. So as an example down here, I have T is 1 millisecond, find the frequency of the clock. Pretty easy to do. Just make sure you can crank through that. If you have 1 millisecond period, you got a 1 kilohertz clock. And on page 157, we're going to look at duty cycle. That's going to come into play as well. How long is the clock high or low? Duty cycle is always defined by the time high divided by the total period times 100%. Here's what we're talking about. There's the formula. The time high divided by the total period of the clock times 100% is the percent duty cycle. So if you have a clock that looks like this, there's a positive going clock. Notice that I'm telling you it's high for 20 milliseconds and the total period is 40 milliseconds. The percent duty cycle is 50%. Make sure you can do that. Next example. Same thing here, except it's negative going clocks. Notice that the time high is a lot longer than the time low, but it's still T high divided by T low. If it's low, 10 milliseconds, and the total period's 100 milliseconds, that's 90 milliseconds high divided by 100 milliseconds times 100%, that's 90%. That's what a 90% duty cycle looks like right here in that second example. That's a 90% duty cycle. This is what a 50% duty cycle looks like up above. And I did another example here on page number 158. That's what a 10% duty cycle looks like. It's high, 10 milliseconds. The total period is 100 milliseconds. Find the percent duty cycle. 10% duty cycle looks like that. And clock pulse timing. We're going to be seeing this coming up too. I want to identify these different clocks. This is one clock running, and these are different pulses of the clock. In relation to one another, let's say this is T. This is going to be T sub 1. This is going to be T sub 2 as time progresses in this direction. Pretty easy to understand. That's just a nomenclature on a positive going transition of that clock. Down here, we're going to give it a little bit different nomenclature because some of our flip-flops, when we get the synchronous logic design, will do this. This is T sub n. Let's don't call it T sub 1 or T sub 2. Let's just call it T sub n, some nth clock. Well, the next one following it is T sub n plus 1. The next positive going transition following the T sub n plus 1 is T sub n plus 2. What if this was T sub n minus 2 here? The next one is going to be T sub n minus 1. The next one will be T sub n. Or work backwards. If this is T sub n, this is T sub n minus 1, and this is T sub n minus 2. Pretty easy to understand. You should understand each of these as time progresses. And that concludes this lecture.